Hi, I'm Bob. Welcome back to 5-Minute Econometrics, a program dedicated to fundamental econometric concepts, estimation methods, and identification strategies. Recall that for a linear model, if the error term has a non-constant variance, we can transform the outcome and explanatory variables so that the transformed error term has a constant variance. We then use the OLS method to estimate the parameters of the transformed model. The estimators, beta stars, from the transformed model are called the Generalized Least Squares (GLS) estimators. Generally speaking, the GLS estimators are the OLS estimators from a transformed model. Because the transformed models satisfy the Gauss-Markov assumptions, the GLS estimators are consistent and efficient estimators of the population parameters. In previous topics, we model heteroskedasticity as a constant sigma squared multiplied by the heteroskedasticity function, known as the hx function, which equals x or x squared. One limitation of these heteroskedasticity constructions is that the explanatory variable x must be positive to ensure that the error variance is positive and increases with x. There are other ways to model heteroskedasticity. The feasible GLS estimation method uses the natural exponential function to model heteroskedasticity. That is, the heteroskedasticity function hx is an exponential function with base e. The error variance equals a constant sigma squared times this heteroskedasticity function hx. The benefits of using the natural exponential function are that it is always positive and is an increasing function. It allows the explanatory variable to take both negative and positive values. Therefore, it is appropriate to use the exponential function to model variance. The exponential function is also very flexible because we can use a linear function of x as the exponent. The parameters delta are unknown. The idea behind feasible GLS is that we use data to estimate the parameters delta. In other words, the heteroskedasticity function, that is the h function, can be estimated with data. Using the estimated heteroskedasticity function hx in the GLS estimation is called feasible GLS estimation or estimated GLS. The estimators are known as the feasible GLS estimators or the estimated GLS estimators. Both the weighted least squares, WLS, and the feasible generalized least squares, FGLS, are generalized least squares, GLS estimation methods. The difference between feasible GLS and WLS is that in WLS, we assume we know the heteroskedasticity form of the error variance, and therefore the weights are known. By contrast, the weights in the feasible GLS are unknown, and we must estimate the weights in the feasible GLS. The feasible GLS can be viewed as a special case of WLS because after estimating the weights, we perform the weighted least squares estimation. There were 4 steps to do the feasible generalized least squares estimation that accounts for heteroskedasticity. In the first step, we estimate the original model by OLS and obtain the OLS residuals, mu hat. We then square the OLS residuals and take the natural log to compute the log of mu hat squared. In the second step, we run an auxiliary regression of the log of mu hat squared on all the explanatory variables in the original model by OLS and obtain the fitted values. In the third step, we estimate the heteroskedasticity function hx. We exponentiate the fitted values. It results in the estimate of the heteroskedasticity function hx hat. The weight we will use to transform the original model to adjust heteroskedasticity equals 1 divided by the square root of the h function. In the fourth step, we transform the original model with the weight. We then estimate the transformed model by OLS without an intercept. The OLS estimates from the transformed model are the feasible GLS estimates. We can also do an alternative auxiliary regression in the second step. It is similar to the method we use in the White test. There are always 2 regressors in the auxiliary regression regardless of the number of explanatory variables in the original model. The 2 regressors in the auxiliary regression are the fitted value and its square term from the original model. We use an example in the textbook Introductory Econometrics, a modern approach, the 7th edition, written by Professor Jeffrey Woodridge. The model relates the demand for cigarettes to income, price of cigarettes, education, age, and whether the person resides in a state with restaurant smoking restrictions. We first run the regression by OLS. We cannot find either a significant income effect or an on-price effect after the OLS regression. Neither the estimate for the log income nor that for the log cigarette price is statistically significant at any conventional level after controlling for other factors in the model. The plots of residuals versus fitted values show patterns of heteroskedasticity. In the Broich-Pagan BP test, we regress the squared residuals on all explanatory variables and obtain a LM statistic of 32.26. The p-value is 0 to 4 decimal places. We reject the homoskedasticity hypothesis. The Y test gives the same conclusion. It provides stronger evidence of heteroskedasticity. The p-value for the LM statistic in the Y test equals 0 to 5 decimal places. Therefore, we estimate the model using feasible GLS. To manually find the estimates, We follow the 4 steps of feasible GLS to address heteroskedasticity. We have already obtained the squared residuals from the original model in the BP test. We generate the log of the squared residuals. Next, we run the auxiliary regression of the log squared residuals on all explanatory variables and obtain the fit values. After that, we exponentiate the fit values. The result is the estimated heteroskedasticity function, hx. The weight accounting for heteroskedasticity equals 1 divided by the square root of the h function. Finally, we use the weight to transform the original model. All variables are multiplied by the weight. We estimate the transformed model by OLS without an intercept. The OLS estimates from this transformed model are the feasible GLS estimates. In addition to computing the FGLS estimates by hand, Stata provides a command that can estimate the heteroskedastic model by feasible GLS. We replace the regress command with the het_regress command. We use the option 2-step and place all explanatory variables in one parenthesis of the het option. It gives the same estimates as we do by hand. I compare the feasible GLS estimates with the OLS estimates. The income effect on the demand for cigarettes becomes larger and statistically significant at the 1% level. If income increases by 10%, a person smokes 0.13 more cigarettes per day, approximately 47 more cigarettes per year on average. The price effect is also bigger, but it is still statistically insignificant at any reasonable level. The other estimates have no substantial changes. Today, we explore the feasible generalized least squares FGLS estimation method to address heteroskedasticity. It involves 4 steps. The FGLS estimators are consistent and asymptotically more efficient than the OLS estimators when heteroskedasticity is present. Thank you so much for watching this video. See you soon. Take care. Thank you for watching this video and subscribing to my YouTube channel. See you next time.